Hello everyone, my name is Tan Under, and in this video, I'm going to talk about VMM Docker CI using QEMU with custom kernel. VMM CI is a little bit different from the usual CI because running an VMM requires special kernel support such as KVM virtio and VFIO. To support these features, we cannot casually patch our CI server kernel unless the kernel code has been tested before. Besides, running an VMM may require special hardware such as IOMMU and PCI devices, which may not be available in our CI server. For cross-architecture VMM CI, we cannot simply use the QEMU user static because it is more of an interpreter and not a system emulator, which means we cannot emulate this hardware right here. Here's an example VMM CI flow. In the green box here, we have our host, which is the CI server, which contains the repo to be tested. We can pass this repo as a volume to the Docker container. Optionally, we can compile the repo inside the container, or we can wait until we are in the QEMU, only then we compile there. To pass the repo to QEMU, we can use 9pfs. Inside the QEMU guest, we can have a custom test service that does compilation or test during the init. Once that's done, then we can trigger QEMU exit through the vert-test MMIO device using the utility called devmem. Using this vert-test MMIO, we can have custom exit code. So the QEMU exit with the custom code back to the container and then container back into the host, which completes our VMM CI. Here's an example Docker image to achieve what we have just discussed. In this example, we are trying to run RISC-V VMM CI on x86 server. In the Dockerfile, we are using multi-stage because we are trying to minimize the size of the final image. In the builder stage right here, we are building the QEMU for the x86 server, and we also build the OpenSBI and Linux with KVM support for the QEMU guest. In the next stage, which is the rootfs builder, we will build a RISC-V rootfs for use in the QEMU guest later on. And in this rootfs, we have a custom test service which will run the test on init. Lastly, we have the final stage where we copy the binary output from the builder stage and also rootfs builder stage. In this final stage, we'll also install the Rust RISC-V cross compiler, and we also have a QEMU CI starter script, such that when we do the Docker run, we can specify the QEMU script to run the QEMU guest. Now is demo time. Using the Docker image discussed just now, we'll see its usage through build or test examples. In the first demo, we'll see the CI build. Since Rust native RISC-V compiler seems to be unstable at the moment, let's do cross-compilation in the Docker container. This is the repo that we are trying to build, and we pass the repo to the Docker container with this path. And then this is the Docker image tag, followed by the command to be run in the container. These last three lines here are the cross-compilation command. And finally, we should take note to change the volume content ownership back to the host, because when we are running in the Docker, we are running as a root. So we don't want to end up having root on files after the Docker run finished. Now let's see the effect of running the command mentioned just now in my computer. I've put the command in the script called docker test.sh. Let's run it. So the build has started and finished. In the next example, we have CI test. This is almost the same as CI build before, but after the cross compilation, we'll start the QEMU guest to run the cross compiled binary, which is the script right here. Inside the container, when we run the QEMU script, it will launch a QEMU guest, and we pass the Docker volume, which contains the cross-compiled repo, to the rust-vmm guest via the IPFS. The rust-vmm guest will boot using the rootfs that we built in the Dockerfile just now. When the guest is booting, it will run the test.service that we installed during the Docker build. And here is the test.service file. It will run a script called testservice.sh. Basically, what this script does is it will mount the repo to be tested, and then it will search for the cross-compiled binaries. Finally, it will run each of the found test binaries. After the test has finished, then the thread handler here will exit the QEMU with custom code. It works by using the devmem command, writing the encoded exit code to this MMIO test address here. Once this write has been completed, then QEMU will exit and we are back into the Docker container. Here is how the CI test would look like. So let's run it. It will first cross compile the repo. And after cross compilation, we'll start the QEMU guest. And finally, you see we have a custom test service which will mount the repo and then search for the cross-compile test binaries and finally run the cross-compile test binaries. In this case, we have passing test result. And so we are exiting QEMU with exit code of 0. Let's check right here. As you can see, the exit code is 0. Next, I'll show what will happen if we have any fail case inside the test. Let's say we intentionally introduce some error into our source code. Let's say we modify the magic number here. And then let's run the test again. So as you can see here, we have the one failing test because we modify the magic number. So as you can see here, there's the error. And in this case, QEMU is exiting with code 101. Let's check it. So yeah, the code is 101. Thanks for watching. The link to the source code can be found in the description below, and the pull request to rust-vmm container is still in progress. If you have any question, feel free to reach out to me via LinkedIn with the link shown here. And thanks for watching. Bye bye.